talk about biopotential signals and ECG and instrumentation amplifiers. So biopotential signals is essentially things like electrocardiograms. So those are electrical signals that control your heart contraction. The electromyogram, the electrical signals that control your muscles. The electroencephalogram, the electrical signals in your brain, and et cetera, et cetera. There are quite a number of them. There's like EGG, electrogastrogram. That's the electrical signals that control your gastric movement. ECOG, electrocortico. I actually don't know what that one stands for. ECOG. Loading, 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 loading. Electrocortogram? Electrocortography, yes, that's electrocortogram. And these just basically have to do with measuring the electrical signals produced by the body for some motion. So cardiogram is measuring electrical signals of the heart. Myogram, electrical signals that could cause muscle contractions. Electroencephalogram, electrical signals in your brain. Those all have to do with neurons, except for the cardiogram has to do with cardiomyocytes. Electrogastrogram, I think it's just the neurons that innervate your gastric region. Electrooculogram, the electrical signals that control your eye muscle contraction, so that's muscle as well, and things like that. So the interesting thing about it, to measure these signals, it's honestly kind of the same type of circuit. So I've kind of made something here. I call it the super simple electrocardiogram circuit, but as of lately, I've renamed it to the super simple EXG circuit, because that X can be a lot of different things. Follow me so far?
Yeah.
Yeah, so there are a couple things you need to consider when you're measuring biopotential signals. Let me pull up my notepad here. And this can go into the documents. Measuring biopotential signals. So I guess we can define these slightly. Biopotential signal, any electrical signal produced by a biological system. In this case, we're talking about humans specifically. The ECG. And so some characteristics of these. So these are essentially the body, in this case, the biological system is acting as a voltage source. And this is a big topic in BME 301 and BME 305. So we'll hear about this at length when you take these classes. BME 301 talks a lot about neurons. So you learn a lot about EEG, ECOG, and you'll actually, EMG, you'll actually build a device to do the EMG signal. And BME 305, we more or less tend to focus on the ECG. And action potentials. So we actually do that quite in length here in BME. And this is like very typical biomedical engineering program. You're going to do one of these. It's always particularly the ECG or the EMG, because frankly those are probably the two easiest. EEG is relatively easy as well. You just have to be a bit more careful about a couple things, and I can tell you more about that here in a sec. So anyway, the biological system is essentially acting as a voltage source. So if we go back to my circuit simulator here, so imagine the biological system acting like a battery, for example. And so see how fast this will load, if at all. Let me let's see, if you imagine I have some sort of signal here, and you can call that ECG. And that's kind of the idea. And it's not a sine wave, it's a complex wave in this case, but that's kind of the idea. One particular thing about the biological system, though, is that it can't produce a lot of current. And so it isn't an ideal voltage source like a battery would be considered. Does that make sense? So you can't use yourself to power your mom's car or something like that. You just can't produce enough current to do that.
Okay.
And so this is, so if you want to get into some of the details, so this is because we have a lot of source impedance or series resistance, and that's from a lot of things that's sort of out of scope of the workshop, but just kind of get you an idea of what you're talking about. So essentially, if this were a battery, a battery can produce quote-unquote unlimited current, right? Because the resistance, internal resistance of the battery is really, really low. So if you do your V equals IR, if R goes to 0, okay, and let's do this. Let's get all engineering. So as R goes to infinity, what's the word? And I goes to 0. Does that make sense? So V is a fixed number. As R goes to infinity, I gets really, really small. So in the case of a battery, well, depending on what type of battery, I'll just do example, AA batteries, R is really small. Generally less than 1 ohms. 1 ohm. There are other types of batteries where the resistance is actually several ohms, but this is an example. In the case of a human body, R is dozens to thousands, to frankly tens of thousands, or even mega ohms. So you can see why we can't produce a ton of current. You follow me so far?
Yeah.
And that's for a lot of reasons, which I'm gonna maybe skip out on some of the details, but at some point, I'll sort of rope you into why that is. And so, because of this fact, because R is really, really high, we need a very particular type of measurement circuit to measure bipotential signals. And so, the characteristics of this measurement system a couple of them is that it doesn't load, and I'll put this, it doesn't load the circuit. So think of it as a multimeter. So I didn't go into this in too much depth at the beginning, but a multimeter has what's called a high series resistance, and I'll probably leave some of this to your 3 or 5 classes so we can get through a couple things here. But a multimeter has a really, really high internal resistance. That way, it doesn't draw a lot of current from the system that you're measuring. So I'm debating whether or not how much detail I'm going to go in. So hold that thought. It doesn't load the circuit. So high input impedance. There's another thing. It rejects common mode noise. That means it's high CMRR, common mode rejection. CMR, common mode rejection. Let's see. Low noise, because biological systems are inherently noisy. And so things like that. So the biggest thing is probably these two here. It doesn't load the circuit, and it has high input impedance. And I can sort of get into a small explanation of why the first one is important. I don't think I went over this when we talked about multimeters earlier, but I will now. So if I have some sort of voltage source, let's just say it's a AAA battery, AAA battery, so 1.5 volts. So your multimeter, I'm going to write a multimeter symbolically, has a very high internal resistance. Depending on the multimeter, can be 1 ohm, can be 1 gigaohms, etc., etc. And so this sort of relates to a voltage divider. So if I put in the series resistance of the battery, or the internal series resistance of the battery, let's say this is our internal, and for the AAA battery, I'll make it 1 ohm, even though it's probably a lot smaller. But let's leave it at that for now. And let me label a couple things here. What's the word I'm trying to use? Equivalent circuit model, non-ideal battery. Well, one of the equivalent circuit models. And I'll draw a box around this guy here. Equivalent circuit model. Alright, so is this sort of making sense so far? So inside of a battery, you can sort of simplify it to a voltage source with a series internal resistance of about 1 ohms, honestly probably even less. And for the equivalent circuit model of a digital multimeter, it's like adding a 1 mega ohm resistor to the circuit. Is this making sense so far?
Yeah.
So if you remember, so this is a voltage divider, right? And so the general form for a voltage divider well, this is actually fine. Let's see if I can get one with the equation. Aha, here we go. You remember us doing this? We have R1, R2, and so the output is R2 over R1 plus R2 times Vn.
Is that, so that's splitting off the current?
Yep, splitting off the voltage, yeah. So we talked about this a couple weeks now, so it has been a while in case you forgot. But it's just 2 resistors in series, one after the other. And so if you're reading the output basically in between the 2 resistors, this is the equation for the output.
Okay.
And so if we translate this to this, you can see that we're having the same issue here, right? So we have a voltage, we have a resistor here, we have a resistor here. So the output, which is this, is the output here is what the multimeter is going to read. That's the voltage that you're going to read on the screen of your multimeter. Making sense so far?
Yep.
All right. So if we go to the equation, what happens if R2 is much, much bigger than R1?
Basically, you're not getting any resistance then on the voltage.
Yeah. So what's V out?
Basically, the in, right?
Yep. Perfect.
Okay.
So if V out, so if R2, in this case, the internal resistance of the multimeter, is much, much bigger than R1, V out is essentially equal to V in. Can you see this number? Is it resolved enough?
Yeah.
Yep. Let's say if my multimeter was really, really crappy though, and the internal resistance of my multimeter was, instead of being 1 mega ohm, it's 1 ohm. Now it's not much, much bigger than the internal resistance of the battery. So when I run that solver, I don't get V in, I get half, yeah. And so this is why your multimeter has a really, really high input resistance, because it doesn't want to load, which means draw current away from. It doesn't want to draw current away from this system. So voltage sources, no, voltage measurement devices should have a high internal resistance. So if this isn't a battery, let's say it's your ECG. Let's do the ECG, and I'm going to make
voltage is real low. We want super high resistance then.
Exactly, yeah, and the resistance we're going to see from the ECG is like 5 microamps. the size of the voltage, and the internal resistance. I'm going to make up a number, but this can be honestly a lot of things. I'll just say it's 1 kilo ohm. Yeah, if my measurement system, is even 2 kilo ohms, and I'm trying to measure this 5 microamps here, you can see that I'm getting some what's called attenuation. The voltage that I'm measuring isn't exactly what it is originally. So instead, we want systems that have resistance, internal resistance, honestly up to giga-ohms. And so that would mean that I'm getting my 5 microamperes passing through. So for that case, instrumentation amplifiers, they're very, very well known for having high input resistance, meaning that this R internal is just ungodly high. Honestly, is the best way to put it. People always say the higher the better, because in some measurement systems for like electrocardiogram or things like that, you can have internal resistances, honestly, even all the way up to mega ohms, depending on your electrodes and all those types of things. And I'll actually go into and explain that a little bit more as well. So you want this to be incredibly high. And so if we look at some example instrumentation amplifiers, this is the one that you have, the AD623. And we go into its data sheet. Loading.
So, quick question on the voltage part.
Go for it.
So, why do we put that massive second resistor there? Is it to like make the current basically dissolve to nothingness after it's read, or?
Yes. So in this case, I'm trying to measure the exact voltage of a battery. So I want that resistor to be really, really high. Typically, when you're measuring something in your circuit, though, let's say I don't know. Let's say you make a voltage divider, and then you're trying to test your voltage divider to see what resistances you're getting. Let's say you just make a random voltage divider for whatever reason. This is probably a little more accurate. Yeah. So what loading means? It means drawing current away from. So because this resistor is really, really high, it doesn't draw current away from this part of the circuit. So loading. So if you don't load it, it means you're not drawing current away from. So like if I said, so a motor is a high load because it draws a lot of current away from the system. Is that making sense?
Well, so say at our normal voltage drive we had there in the beginning, so if we don't have that massive second resistor there, is the voltage just going to be inaccurate because of like vehicle's IR from the internal resistance?
If we don't have that massive, let me go back.
So the whole point of that second massive resistor is to basically offset the internal resistance in our source?
I don't know if I'd use the word offset.
Or I guess like make it so it's not a different reading when we measure it.
Exactly. Yeah. So if this wasn't massive, if it was 1 ohm, now the current flowing through here is going to be equal to the current flowing through here. So you're going to get some voltage drop here. So you're not actually reading the 1.5 volts from the battery directly.
Okay, that makes sense.
So if we look at instrumentation amplifier, and I'll just search input impedance, it'll show up. You can see the input impedance of this guy is like 2 giga-ohms. So that's really, really big. And everything has some sort of capacitance, so that's why you see this means 2 giga-ohms in parallel with 2 picofarads. So that's kind of an example characteristic of a typical instrumentation amplifier.
Okay.
And so another thing that I sort of pointed out, wave my hand around a little bit, is it rejects common mode noise. So biopotential signals in particular, let's see how I want to do this. So our bodies act like antennas, so that they just pick up what's called electromagnetic interference. So biological systems can act as antennas. One of the most common ones is power line noise. So that's 60 hertz in North America and 50 hertz in Europe. And so this is the power that's being delivered to your house and your apartment and all that. That's sent in as an AC waveform, and the frequency of that AC waveform is 60 hertz in US and 50 hertz abroad. So because your body acts like an antenna, if you actually touch the probe of an oscilloscope, you'll actually see just a 60 hertz waveform showing up on that oscilloscope. So let's see if I can find a YouTube video of it actually. 60 hertz noise, body, oscilloscope. So imagine, people passing Wi-Fi signals all around you, and like you actually taking on that Wi-Fi noise like an antenna. Yeah, it's kind of wild. These aren't the right type of stuff. Whenever you're here on Wednesday, I can show you, like, if you just touch the probe in the oscilloscope, you can see that it'll start actually picking up the noise from you. Video might take a while to load, so I might just have to show that one a little bit later. Does that make sense so far?
Yeah.
And so with biopotential measurements, you're often measuring the voltage drop across two different points. So our heart has a polarity. The electrical current goes from the top right of your heart down to the bottom left. That's just how the heart is shaped, and how it goes. I don't remember the physiology of it exactly, but the heart has a positive pole, which is the top right of it, and a negative pole, which is the bottom left of it. So the electrical conduction actually goes from top right down to bottom left. And so what you're doing is you're measuring the potential difference between the top right, or the positive side of the heart, from the bottom left, which is the negative side of the heart. You're measuring the voltage drop across those 2 points. And so you actually have two measuring probes, like you do a voltmeter. You take a multimeter, you put the positive probe on one side of your circuit, and you put a negative probe on ground. You do the same thing when you're doing biopotential measurements.
Wow. Okay.
Yeah, it's pretty dope. And so because your body's acting like an antenna, you have power line noise. Basically, I don't want to use the word radiating, but radiating all throughout your body. And so that power line noise will be picked up by the two probes of your instrumentation amplifier, and it will be common to both signals. And so having high common mode rejection ratio, or high common mode rejection, will eliminate that 60 hertz of power line noise from the signals you're measuring. And it's probably easier to show rather than talk about it, because somewhat talking about it is a little bit abstract. I don't have a wonderful, yes I do.
So is the way you get rid of that noise is like through like filters, like a notch filter or something? Or?
Exactly. Yeah, a notch filter would be perfect. So the instrumentation amplifier helps a bit, and if you want to get rid of more, you'll use stuff like a notch filter. So this has a good show of what the noise looks like. So if you're doing this on the Arduino or whatever, it will oftentimes look like what you see on the bottom left here. And so if you did a frequency analysis of this, you'll see that the primary frequency component is around 60 hertz. So a instrumentation amplifier helps reduce this noise to some extent. You'll need to do extra filtering to get rid of it more, but instrumentation amplifier does it really, really well already. And so this is a pretty good example too. Yeah, this has a lot of noise. So all that there, all that fuzz, is 60 hertz noise. Ideally, you'll want something that looks like like these. These are pretty clean waveforms. but in reality, you start off with something that looks like this.
Man, so if we were like in the desert, away from like all these electronics, would we still have noise then?
Not as much, but you'd have to be in remote desert because it does radiate several miles. But yeah, it would be a lot less. So if you, let's see, the best. Honestly, like for instance, if you have some sort of a motor that's being plugged into something that takes a lot of current that's being plugged into the wall, and you stand closer to it while you're measuring your ECG or something like that, you can actually see the increase in the 60 hertz noise.
Wow.
Or if you like touch something, like I do this often. So sometimes I'll touch something that's attached to something that's producing a lot of noise, and you can see the increase in the noise in the signal. Yeah, it's really cool when you actually see it. So maybe I'll show you. Maybe I might show you tomorrow. Or maybe I can put together a pretty quick setup.
Okay.
But yeah, so you want a certain amplifier that will get rid of that type of stuff, and an instrumentation amplifier does that really well. And it does that because it essentially subtracts. So because you're looking at the difference between two signals, I think I have a good video on here. Not video, but diagram. But you see here I have electrodes on both wrists. So my instrumentation amplifier is actually subtracting this. So this part is on the positive side of the heart. So the positive side of the heart is to the top right. So my right arm is towards the positive pole of the heart, and my left arm is towards the negative pole of the heart. So the instrumentation amplifier is actually subtracting these two signals, but they both have 60 hertz noise on them. So if you subtract something, if you subtract the same signal from itself, you basically get zero, right?
Okay.
Yeah, that's kind of that gizmo. So if I can write it symbolically, VECG plus, and then you have
Wow, so your potential difference from your heart like translates all the way down to your wrist then?
Yep. Mm-hmm.
Man.
Yeah. So in what's the word I want to use? In aqueous solutions, uh, let's see if I can find a diagram. Electrical current in water. So our bodies are, I don't know, like 60 to 70% water or something like that. So in aqueous systems, or more, I have no idea what it is. Let's see if I can find a good electrical currents. Water radiates. Not a good, no. I can't, this isn't great. No, that's not exactly right. This isn't right either. Anyway, so in aqueous systems, electrical current actually radiates. Sort of like if you sound symbol. So like if you imagine the sound symbol here, let's say if right here I put an electrode and I start actually pumping electrical current through it, electrical current would actually radiate concentrically around the source.
Okay.
So if you imagine my heart, being that source of electrical current, the electrical current will actually radiate from, my heart, all the way throughout the rest of my body. So that's why you pick up the ECG on your wrists.
Okay.
You can put it on your back. It radiates in all directions in 3 dimensions. So you can put it on your back. You can put it on your leg. As long as it's sort of across your body, and that's kind of where you'll get the best signal. So you can be on the more positive side of your heart versus the more negative side of your heart. You can still pick it up. Yeah, pretty cool stuff, huh?
Yeah, that is interesting. So when people say they're like reading your electrical signals in your arm, so do they have to have like two electrodes in reading the potential difference?
Yep, because typically these measurements are differential signals, so you have 2 electrodes. There are some techniques you can actually do 1 electrode, but that one, because you don't have the subtraction of the 60 hertz noise, it will often be a little more noisy, but it is possible in some contexts. And useful. Some when you have like the 12 lead ECG where they put like 12 electrodes all around your chest, some of those electrodes are actually single-ended, so it's not a differential, it's just a single point measurement. And that has different diagnostic value than doing differential measurements.
Okay.
But yeah. So if I do it symbolically, you do ECG plus, ECG minus, positive side of the heart, negative side of your heart, and you have V 60 hertz, V 60 hertz. You know, 1 electrode might be V ECG. I don't know if I can do superscript. I'll do plus. And so if I'm doing a subtraction, so 1 electrode on the positive side of my heart, this is the signals picking up, the plus side of the ECG, quote unquote plus side, and the 60 hertz noise, and the other electrode is picking up the minus side of my ECG, quote unquote, plus the 60 hertz noise. So you can see if I do this math, it comes out to basically be VECG plus minus VECG minus, because the 60 hertz noise is common, so it gets subtracted out.
So then if you're just having 2 electrodes in, you don't really even have to account for the normal because it'll get subtracted out?
Yep.
That is different? Okay.
So typically, though you'll want to use 3 electrodes because your 3rd electrode will be a reference. So typically you'll at least do 3 electrodes, although like devices like chest strap heart rate monitors actually only use 2 electrodes because they create a virtual reference.
So then why do we have to use filters then if it already gets taken care of on that?
Yeah, so it doesn't get taken care of completely.
Oh. Okay.
So like this might be V 60 hertz bigger, this might be V 60 hertz smaller. So you still get some difference there, and that will get amplified.
Okay.
It's the same frequency, but it may not necessarily be the exact same amplitude. So there's still going to be some difference.
Okay.
Making sense?
Yeah.
So that's why we use instrumentation amplifiers. They have high input impedance. They're differential measurements, so they have high common mode rejection ratio, and they're low noise. And they're just specifically designed to be very, very well fine-tuned. So they have low noise. But the first 2 are kind of really the biggest parts of them. And I'll actually show you what it looks like, so you can see why it does the way it does. Instrumentation amplifier, and I'll compare it to a couple more things. So the classic construction of an instrumentation amplifier is 2 buffered inputs and a differential amplifier. Did we talk about buffer amplifiers at all? I thought I may have mentioned.
It doesn't ring a bell, but we may have, and I might have forgotten.
Yeah, that's fine. So you can go over a little bit more here. So with a buffer amplifier, V in is equal to V out. So I'll go ahead and create one. So essentially, if I have some input voltage, tied to the inverting pin, and then actually I want to flip this, tied to the non-inverting pin. And so what this does is V out is equal to V in. I change it to 10. I still get 10 on the output. And so amplifiers have high internal resistance, so you imagine this just being a multimeter. So this is you measuring the voltage across something with your multimeter. So V out is equal to V in. Make sense?
Okay. Yeah.
And so then we have differential amplifiers, which they do exactly what they sound like they do. I'm trying to find one with the equation. That's fine. That's fine. So you essentially take two input voltages, V2 and V1, and subtract them. And based on how you configure the resistors, you can get certain different sets of gain. So this is basically saying V2 minus V1 times some gain. And so to get an instrumentation amplifier, we essentially combine a differential amplifier with a buffer amplifier to make my favorite amplifier, to make this guy. So this part is a differential part. You can see that this is more or less equivalent to this. It's just rearranged slightly differently. Can you see that?
Yeah.
And then this, particularly this part, is more or less equivalent to this. Can you see that?
Yeah.
And this is kind of a special resistor network that makes it easy to set the gain. And so different instrumentation amplifiers, the way they're designed such that you can set the gain with one resistor. And that's what this RG is. And that's just kind of, they say typical, because what will happen is in a manufacturing procedure, they'll actually make all these resistors the same. R1 is equal to R2 is equal to R3 is equal to R2 is equal to R1 equal to 3. Or they can like make these R3 different from these guys, but typically they'll oftentimes make all these resistors equal to each other. Because if you imagine this on a production plant, if the machine only has to make the same thing over and over again, it'll be more accurate than if it's trying to make one thing and then something else. And then this RG is set by the user, and that way the user can select the gain.
So this is kind of a beginner question, but does gain then, like how much voltage it would gain from the input to the output?
How many times?
Okay.
How much it will amplify it?
Okay, amplify.
Yeah. Gain, amplify. Those are the two words we will often use. And you can actually see that. So this is the 8623. This is the instrumentation amplifier you have, and you can see the equivalent circuit here. So you can sort of ignore that part. But if you focus in on this part here, can you see my cursor?
Yeah.
And then we go back to here. You can see that they're identical.
Okay.
Yeah. And so for this particular part, the manufacturer made all these resistors 50K. Again, because it's just a manufacturing process, if the machine only has to make one type of something, they can fine tune it so that it makes that one type of thing very, very accurately. And so that's somewhat of a just kind of a manufacturing benefit.
Okay.
And then you will set the gain with this RG. And that's on pins, and this one I think 1 and 8, yeah. All right, let me get some questions. What you got?
So when you say gain, like, I know you said it's amplifying. How can you just like gain voltage, I guess?
Yeah. So I probably, did a bit of hand waving at this part. So this, you'll go into a lot more detail with this in BME 305, but that just kind of goes into how amplifiers work. And so I'll show you an example here in a sec. So this amplifier I'm about to make, it's called an inverting amplifier. And it'll take me a while to make it just because the feed is making things kind of slow. I'll make this, one's fine. So this is called an inverting amplifier. It's one of the most common types. I'll make these, this is a little bit bigger, 10K and 10K, and I'll tell you, just let you know, this has a gain of 1. And I'll show you with the simulation. The outputs are my input is 1, my output is also 1. Well, again, it has the gain of -1. That's the inverting part. And so if I make this -2, so it has a gain of -1, so it should be +2. If my input is 15, it has a gain of -1, so it would be -15. And so the way it does that is, there is a current, so because you have a voltage source here, and a resistance here, you're going to have a current flowing through this resistor. And I'll change this back to 1. I'll actually change this to 1K to make the math easier. So going back to our amplifier rules, I know it's been a while and I probably didn't go into too much detail. So the voltages of the two inputs of the amplifier should be equal. So if this voltage is ground, is 0, which it is because it's connected to ground, this voltage should also be 0 or ground, or close to it. Does that make sense? So that's just a rule of how amplifiers are designed. The input voltages are equal to each other. So if I run this, you can see this is 0 volts, and this is 3.5 microvolts, which is pretty close to 0.
So you're putting the positive voltage into like the negative side of the amplifier?
Yes.
Is that the inverting part of it, or is that how an amplifier normally works?
This is how an amplifier normally works, and just based on this configuration in particular, just gets you an inverted voltage.
Okay.
So you can see that both these inputs are 0 or very, very close to 0. So now if this is 0 or 3.5 microvolts, and this is 1, we're going to get some current flow through this resistor. Do you agree with that?
Yeah.
All right, and so we can see that, so it's going to be 1 volt minus 0, or 3.5 microvolts or whatever, divided by 1 kilo ohms. And that's going to be around 1 milliamp. And so that's what we get here.
Okay.
It should be positive. This is the way. Does that make sense?
Yes, I just am, so like, voltage, right, we say that it's positive, the flow of electrons is positive, right?
Mm-hmm.
And then like our ground would be our negative then?
Our ground is 0, so this just means, so the negative and positive just denotes direction. So let's see, so positive, well, so you're basically asking how do we get a negative voltage, right?
Yeah.
Let's see if I can schematically draw this. So the sign just denotes direction. So essentially, if the current is flowing from the positive side to ground, then it's a positive voltage. If the current is flowing from ground to the negative side, then it's a negative voltage. So the ground is the ground is sort of just a reference point. So the way people often explain it is, if I have a tree or some point on a hill, so this is a hill or ladder or however you want to put it, and so if I have some point there, right, and I consider this bottom part is my ground, we can say that this point is 2 steps above ground, so positive 2 elevation points or something like that. Is that making sense so far?
Yeah.
But if I consider this part my ground instead, it's actually at 0. So if I were to move it here, and I consider this part my reference point or my ground, then it's actually -1 below. So it's just basically what's your reference point. So some people, instead of calling it ground, they'll just say reference, and they'll use those two things sort of interchangeably.
Okay, so is that why it's called VRAF sometimes? Or is that something?
That might be something else, but you're creating a separate reference in that case.
Okay.
So in the case of a battery, battery, you have an anode and the cathode, right? Oxidation occurs at the anode. Oxidation involves loss, so electrons actually flowing from the anode to the cathode, right?
Mm-hmm.
So a battery only has a positive 9 volts or a positive 1.5 volts or a positive 3 volts, etc., etc. If I put two batteries in series, let's say it's two 9-volt batteries, kind of stacked on top of each other, where the positive side of one battery is touching the negative side of the other, right? And I consider this part my reference because these two are connected. Let's say this is my reference point. Ooh, actually. Right?
Okay.
So this is 0 volts. It's just a reference point. And actually, I can actually probably draw this in circuit a lot easier. Well, Circuit Lab actually may not allow me to do this. It actually may not allow me to do this. Give me 60 seconds. Is your image of this okay?
Yeah.
Okay, so if I just stack two 9 volts, not directly on top of each other, but such that the plus side of one is touching the negative side of the other, and I consider that point of contact my reference point, then the negative side of the other battery, if these were 9-volt batteries, is now negative 9 volts, relative to this reference point. And the positive side of the other battery is now positive 9 volts, relative to this reference point.
Oh, okay.
So that's sort of the same thing you're doing with amplifiers. So then when you're power, so some amplifiers, I don't know if I mentioned this too much, but some amplifiers are, you'll see this thrown around, single supply op amp versus dual supply op amp. And that's sort of what they're referencing. So they have a reference point and then some voltage below the reference point and then some voltage above the reference point. And so that's how you get a negative voltage. It's just relative to some reference point.
Okay.
So I mean, I could even do this with a plus 9-volt battery, just one 9-volt battery. This gets a bit more tricky because I'd have to create it somehow with my circuit. But I could split this 9-volt battery into 4.5 negative and 4.5 positive with some fancy circuit designing.
Okay.
Are we doing okay so far?
Yeah, that definitely cleared that up for me.
Okay.
Because my physics class, it kind of went over it really quick, and I didn't quite catch it.
That's fine. Alright, so we're going back to the amplifier. So if we have 1 volt, flowing through this 1 kilo ohm resistor, you get 1 milliamp, right? So have you taken Physics 241 already?
I'm finishing it up right
Got
now.
it. So they talk about Kirchhoff's current law.
Yep.
Yeah, so if one current flows in this way, then you must also have a current flowing where?
But they have to be equal and opposite, right?
Equal and opposite, yeah. So you have one flowing here as well.
Yep.
So if this, do I have 1 milliamp here, then I'll also have 1 milliamp here. And it might flip the signs. Oh no, there it is. And it's and depending on this thing, sometimes I'm a little confused where it's referencing the direction. So right now, just focus on the magnitude, not necessarily the sign. So I don't know if you can see this somewhat symbolically. Let me name a couple things so we can talk about it a bit more. So, do we agree? Do we agree that this point is 0 volts based on the simulation and the rules of the op amp?
Yes.
So if this point is 0 volts, the input voltage, the two inputs of the op amp have the same voltage. So if this is 0, then this must also be 0. And we ran the simulation, and it gave us like 3.5 microamps, which in this case is close enough to 0. And then, so if we also have 1 volt here, you know that this is a positive voltage, so the current's going to flow this way. Is that how they taught you in physics?
Yeah.
Okay. So that's fine enough. You have some current flowing that way, and then you got some equal and opposite current flowing through this resistor. That's also 1 milliamp, right?
Mm-hmm.
So if this point is 0 volts, and you have 1 milliamp flowing this way, then this point must be minus 1 volts. That way you can do 0 minus minus 1 divided by 1,000 gives you 1 milliamp. Did they do the whole Kirchhoff's? Do they show you the KCL equations where you do something like this? 1 volt minus 0 volt divided by 1 kilo ohm is equal to, I don't know, 0 volts minus V minus X divided by 1 kilo ohm. Does that ring a bell at all?
Not really.
Okay, but so what we're doing is if we have 1 volt minus 0 volt equal to 1 milliamp, right? Then we must also have 1 milliamp here. So the equation for that is 0 minus V out divided by 1,000 equal 1 milliamp. And then you just solve for V out.
Okay. I guess, yeah, we kind of do that when we're comparing like the different loops in a circuit.
Yep.
Right?
Yep. That's typically when it happens. You didn't use op amps, but you just used like our circuits. So 0 minus V out divided by 1,000 is equal to 1 milliamp. So V out must equal minus 1 volt.
Okay.
Does that make sense?
Mm-hmm.
Okay. And so that has a gain of 1, well, minus 1, because V out is equal to just the opposite of 1. But instead of making this 1 kilo ohm, and I'll actually go to Wolfram Alpha real quick, because I like Wolfram Alpha for this. Let me get rid of some of these other ones. Let's not go too far. Alright, anyway. So we have 0 minus V out. Instead of putting V out, I'll just put X divided by 1,000 is equal to 1 milliamp. And so X is equal to minus 1. See that?
Yeah.
Alright. So now what happens if I change 1 kilo ohms to 10 kilo ohms? Now this is still 1 milliamp because 1 volt minus 0 over 1,000 gives you 1 milliamp. And so because of Kirchhoff's current law, you have equal and opposite. If you have 1 milliamp flowing this way, you must also have 1 milliamp flowing this way. But instead of having 1 kilo ohm, now we have 10 kilo ohms. So I'll just make that switch here. So 0 minus V out, 0 minus V out, I'll just put X in Wolfram Alpha, divided by 10,000 now instead of 1,000. And that must equal 1 milliamp. And so the answer to that is now minus 10. So if I run it through the simulation, we get minus 10. And that's how you get gain.
Okay.
And so the equation, so the general equation for this type of amplifier is V out is equal to minus RF over Rin times the in. So in this case, that's minus RF is 10 kilo ohms, Rin is 1 kilo ohms times 1 volt, and in the previous case, it was 1 kilo ohm over 1 kilo ohm. Does that look good?
Yep.
Yeah, so this is an inverting amplifier, and that's kind of just a standard equation. And so basically, being able to manipulate the orientation of the resistors, where your source is going into, the size of the resistors, all that, you can get different gains. And that there are thousands. There are basically endless configurations of amplifiers you can imagine. But the basic ones are, say, the most fundamental ones are probably buffer amplifier, inverting amplifier, non-inverting, inverting summer, differential. These are the ones we'll do in 305. Differential. And those are probably the most basic ones that you can basically derive everything else from that. Questions?
So the triangle, right, the amplifier, or is the triangle technically the sort of op amp then?
Yeah, the triangle, op amp, amplifier, same thing. So the triangle is just the circuit schematic representation for an operational amplifier.
Okay, so within that triangle, there's basically another circuit going on.
Yeah, there's a ton of stuff.
Okay.
And that's ECE 255.
Okay.
Yeah, but that's outside the scope of even BME 305. So that you'll learn in Intro to Electronics. Basically how amplifiers are made.
All right.
And it's been a while since I've taken that class myself. So, but basically, it's a combination of transistors. And you can actually, some manufacturers will actually publish the design of their amplifiers. So for the amplifier we'll use in BME 305, it's the LM741. Oh, they may not have it in theirs. Some people do. Okay, got it. This is what it looks like on the inside. And so these are just various sets of transistors. Again, I've taken that class a long time ago, so I probably couldn't reproduce this myself at this point.
Wow.
Yeah, there's cool stuff though. Sounds good?
Yeah.
Yeah. So I think we got off on that talking about gain, right? When we talk about instrumentation amplifiers.
Mm-hmm.
Yeah, so that's how you can get gain with one amplifier in particular. There are others. And so a non-inverting amplifier looks like this. Oh, actually, Wikipedia has a good page on amplifiers. And it has a good list with the equations of the various types, of the most common types. Well, it used to at least. Yeah, this is kind of it. So non-inverting, sort of oriented like this. And the equation is here. Then it has inverting amplifier, the one we just did here, and the equation is this. Then we have, it usually has more. I thought it had more, but I guess it only has those two. So you have like inverting summer and some of the others that I listed over here.
Okay.
And so the trick is knowing which type of amplifier you need for the given situation, how to configure it, and there's sort of like endless possibilities on how you do that, to be honest. But there's some typical configurations if you're trying to accomplish certain things.
Yeah.
Anyways, I think back to any more questions, lasting questions?
Nope.
So anyway, so instrumentation amplifier, basically if you just did if you solve the theoretical output equation for this, you'll see that the gain depends on Rg if you make all these resistors, other resistors, equal to each other. And so some instrumentation, well, most of them will actually tell you what the equation is, because that's how you need to know where your gain is. And so actually in your BME 301 class with Dr. Irithoki, he'll actually make you derive this equation and show him how you get to this. But that's kind of outside the scope of the workshop. But essentially it comes down to 1 plus 2 times R over Rg. So R in this case is 50K, so 2 times 50 is 100K. That's where it gets this.
Okay.
Alright, so we talked about instrumentation amplifiers, why biopotential signals, why we use them, what are they, how are they built, constructed. And so we talked about biopotential signals a little bit, which you're probably already familiar with. Basically, everyone's more or less heard about the ECG at this point of their lives. We talked about the electrode configuration. You just want to put it on opposite sides of your body or just opposite sides of your heart. And so I guess we can go into building it. And then once you build it, you can take a couple pictures and I'll sort of look at it just through the screen. And then when you're back in West Lafayette, I can give you some electrodes and you can actually test it and measure your ECG yourself. Does that sound like a plan?
Okay, yeah.
All right. So this schematic is really all you need here. I can redraw it in Fritzing, but this is kind of it. You can generally, honestly, probably see it just with the instrumentation amplifier itself. But oftentimes, you'll want to add a bit more gain just to make it a bit more visible. A bit more gain and a bit more filtering just to make it a bit more obvious.
Okay.
So you should have an AB623. So actually, let me ask you this. So did you pull apart the circuit on the breadboard as is already with the pulse sensor circuit?
Everything's still intact, but I can take it apart.
Do you want to keep that intact and then I can debug it when you're here and then we can build the ECG later or what? It's up to you.
It's not that important to me. I can take it apart if you want.
Okay, yeah, it's up to you. So I'll put together this Fritzing. I'll sort of do it live, so you'll kind of see as I'm doing it. But it shouldn't take me too long.
Yeah, I wish I had those. I don't know what you call them. Like the cables that are real flat, stay flush to the fretboard.
Yeah, the pre-cut jumper wires.
Yeah.
Yeah, those are my favorite. Those I just buy them in the bunches on Amazon. Honestly, every time I run out, I just buy another kit. That's why I'm poor now because I've bought way too many electronics things. I can still pay my rent.
About a potential project.
Yeah, what's up? What you got?
So, I this might sound stupid, right? But so I was trying to like Google around, find stuff, and I thought it'd be cool to try to make make a breathalyzer. And
Nice.
And then have some sort of locking mechanism with the breathalyzer.
Yeah, that's a very popular project for a couple of my students. I take instrumentation in undergrad. They should have some pretty cool instructables.
Yeah, I was looking around and because basically the idea was I wanted to make like a 3D print a little plastic container, and you pass the breathalyzer test, right? It opens the container.
Mm-hmm. Yeah, I like it. Are these my kids? I don't know, but yeah, there are a ton of examples of how to do that. And a typical sensor is this MQ3 sensor that SparkFun sells.
Yeah, that's the one I have marked down.
Let me get rid of some of these tabs.
So when you do a PCB,
Mm-hmm.
what all, when you print it, what all will it include? Like, is it basically just the running of like how your wires would be like, or can they actually print resistors on there, or have them already on there?
There are actually like special things where you can actually print the resistors on there, but those are a lot more expensive. But the standard service is just the wires running everywhere.
Okay, and then you like solder on whatever else you need on there.
Mm-hmm. So it'll come out looking like this.
Okay. Yeah, I think Jason got our PCB for the Mind bracelet.
Oh, cool. Yeah, he's leaving soon.
Yeah, I think he said he's gonna solder all of it on, and I gotta pick up all the Mind supplies from his apartment.
Alright, let's try this again. Oh, I might just build it on this. So the instrumentation amplifier you have is the AD623. So make sure you use that one and separate that from the MCP 6004, 6002 rather. So I'll label them on my side. Alright, well. Alrighty then. And stop doing that.
Yeah, I think I'll just hold off on what do we call this again? The Bioelectric Amplifier, I guess.
Mm-hmm.
And I'll just keep the pulse sensor, I guess it is.
Sure.
Yeah, I'm not sure if I can attend the meeting tomorrow because that is like the night before I have to move in, and my physics final is the day I move in at 1 p.m.
Oh, that's
so
rough.
Yeah, I gotta like study, and then I gotta like break down my desk and all the computer stuff.
It's okay. That's alright. I'll actually just finish building this, so that way whenever you're ready to, you can build it. And then whenever you're back in town, just talk to me. We can work on a pulse sensor, and I can give you some electrodes for you to test this guy out whenever you're ready. I can also just give you a breadboard. I have like millions of these, so
Okay.
I can give you a spare as well.
All right.
Yeah, that was more or less all from me today. So we kind of went over the basics and the important aspects of it. But it's instructable. It kind of lays out a lot more things as well. But it was the instrumentation amplifier is really kind of all you need, honestly.
That went on, and so I went on like that. So they brought stuff. They were talking about how they were reading the electrical signals of a guy's like shoulder if he was missing his arm.
Mm-hmm.
So they could read it, and like if he thought about moving his hand, they could read the signals from his shoulder and actually build an arm that would move according to it. So how do they read those signals? And like, do they just put two electrodes very close to each other on his shoulder, or?
Yeah, so those are looking at the nerve impulses. I guess he was amputated, right?
Yeah.
Yeah, those are looking at the nerve impulses on what would have been his muscles. So the nerves that innervate your muscles, they just attach electrodes to those nerves. And so those could have either been single-ended or differential. Maybe just looking at one end of the muscle, the nerve to the other as it propagates down the shoulder. But yeah, that's the basic idea. So
if you put like say an electrode on your arm, then you won't read the nerve signals, or you will.
So if I put it directly on, so that goes into what's called surface EMG. So if I put the electrodes on the surface of my skin, as opposed to actually, cutting open my arm and touching the nerve individually, when it's on the surface of my skin, I'm getting the sum of the electrical signals. And so so what that will give you is that will let you know when the nerves receive an impulse to your muscles to tell them to contract, or relax, and you can actually take that information and do stuff with it.
So in your photo, when you have the electrodes on your wrist reading your heart signals, are you also reading your nerve signals then as well?
The nerve signals for my muscles?
Yes.
I could be. Yep. So if whenever you get this ECG signal, and I don't have an image of it here, and you actually start flexing, you'll actually see the EMG signal, electromyography, which is the nerves that innervate your muscles. You actually see that signal bleeding into your ECG signal.
Okay.
But in this setup, the way I have it configured, it's ideally for ECG, but if I start to flex my muscles, I'll actually start to see components of the EMG.
Wow, okay. So when people try to look at your brain signals, they just have like 1,000 electrodes on your head?
Yep. And so I did this for a class of mine a couple weeks ago, and it's a pretty popular hobby product too, honestly. It'll take a while to load up, but it is there. Me following Power Rangers, childhood memories.
Did they make them speak for me?
I'm not sure. Hopefully, yeah. So I have it on. So these two are on my eyes. I have a better one.
You play Magic or just Yu-Gi-Oh?
Yu-Gi-Oh. I don't actually play. I just like bought a random kit the other day from Walmart because I was feeling nostalgic. These are okay, I guess. Yeah, I'll just go back to this one. Yeah, so these two are around my eye to pick up my EOG, the muscles that innervate my eye muscles to know when I'm blinking. And there's some in my head you can kind of see back here. But for classic EEG, for research applications, they get even more crazy, which is all this.
Oh, wow. So when we have those, we have like a circuit with like the amplifier for one electrode. You just have to have like 100 of them?
Yep.
For 100 of those? Oh, okay.
So these instruments are rather large, but it's basically the same thing repeated.
Wow, and then they probably incorporate all those circuits just in like a box or some sort of machine. Okay. Dang.
Yeah, so you'll actually build this for your BME 301 class. And you can do this with a super simple ECG circuit too, frankly. Just not only one channel at a time. So these will be called like maybe this is like 256 electrodes. The one that you'll make is like a one channel biopotential signal device, but you can make multiple channels if you want. For the thing I was doing here, I had at least two channels. So I was measuring my eye movements, I was measuring parts of my EEG, and I was also measuring my ECG as well. So I had a three channel system going.
So someone proposed last year's Mine as an idea was like a portable EEG, but that probably isn't possible, right? Because you have to have so many like circuits for each of those.
It depends on what you're trying to do. So the more electrodes, the more spatial resolution you can get. So you can get signals that are localized to certain parts of the brain. But if you're only looking for like basic signals like blinking, cognition, awake, you can get away with smaller systems. Like this gizmo here, which is maybe 12, 13, 14 electrodes. These gizmos, well, this one's actually a nice view. This one's like 4 or 5. So it just depends on what you're trying to measure. If you want like super high spatial resolution, it would be pretty impractical because you need like 256. But if you only need a couple things, so certain signals are going to be localized to certain parts of your brain because certain parts of your brain handle certain cognitive tasks. So if you don't need a ton of spatial resolution, you can do a lot with just like a 2 or 3 channel system.
Could you have it like store the data and then at one point plug it into something to start processing all that data that was recorded?
Yep. Like for me, I stored it on an SD card and then opened it up in Excel and processed it there.
Cool.
Yeah, and I was able to detect my sleep patterns, so that was pretty cool.
Oh man, so wow, that is really cool. Huh. So when you do all this, are you always using Arduinos, or do you have like some very specific microcontrollers you use?
No, when I was doing it, I was just using an Arduino. It was just a slightly beefier one, but it was just an Arduino nonetheless.
They have like SD card readers for it. So.
Yeah, I had just had a separate SD card attachment.
Okay.
But you can find Arduinos that have like SD card shields or whatever. So popular one.
Yeah. Did we ever take CME classes about like coding or specific stuff like that?
Not really. So in your BME 301 class, you'll code the Raspberry Pi. It's not really a microcontroller, but I guess it's somewhat close enough. In BME 305, we're trying to add elements of Arduinos, but you don't really get too much, to be honest. If you want to do some microcontroller stuff, I'd recommend the ECE class. I think it's ECE 362.
Okay.
That'll get you, because the Arduino is a sort of a learning guide. So if you want to do things professionally, it's good to like know how you'd actually do it in industry. And so Arduino isn't necessarily poised for that, but it shows you the basics. But if you take a class like ECE 362, you'll kind of get a fundamental basics of how things are really done in industry, and then you can port your abilities into different contexts.
Okay.
Yeah, but you can get some. Go ahead. Sorry.
Oh, yeah, I've sort of been confused on the Raspberry Pi. Like, why is it so different from an Arduino?
So it's a computer. It's like me sitting here and coding on my Mac. It runs Linux. That's like an operating system. Yeah, so imagine like you sitting at your computer. What are you doing now? C. And what environment do you program in?
Yeah, C.
Yeah, what IDE, integrated development environment, do you use?
Oh, honestly, I'm not quite sure what that is.
Got it. But like if you're doing Java, you could use Eclipse. So if I was doing iPhone apps, I would do Xcode. If I was doing Android apps, I would do Android Studio. So the Raspberry Pi is an operating system. So imagine it just like your computer, your PC, or Mac. That's what it does. Versus a microcontroller is more. It's for running. What's the word I want to use? It's more generally used for inputs and outputs. So if you don't want to run something like MATLAB, you want to just take in certain inputs, do some processing, and then output certain, and then make something do something, like run a motor or turn on an LED or send it over Wi-Fi. A microcontroller is a lot more built for that versus something like a Raspberry Pi, which is an operating system, does not do things like keep time very well because it's not really made for that. So for the microcontroller, I could say, I want you to sample this signal or do this process once every 10 microsecond. I can't do that very, very easily on a Raspberry Pi.
Because you need to get a few things then to run on a Raspberry Pi.
You can work around it. You can sort of make it do it if you want to, which is what Dan does for your 301 project. But it's not necessarily designed for those types of things.
Okay, I saw people putting like emulators on and stuff.
Yeah. so it's made for things that you would imagine a computer doing. It's not necessarily made for something you would imagine a very timed event doing.
Okay.
Like image processing, that's like a very, intensive process. So you leave that on something like a Raspberry Pi. But like controlling peripherals, like getting information from sensors, and then like outputting to certain peripherals, you do that on a microcontroller.
Okay, and you just like solder things on a Raspberry Pi as you would an Arduino?
Yep. So that's what you guys do in your BME 301 project. Let's see if I can. I don't know if I can find a picture on YouTube on the internet, but that's what you guys will do. Yeah, I can't find any pictures of any one circuit. Actually, I might. I don't have a picture, but when I find one, I can send it to you.
Okay.
What else you got?
I can't think of any more questions.
Yeah, these are good questions, dude. Sounds like you're thinking a lot.
Yeah. I have one more question. So in Physics 241, we learned. I mean, it seemed like we learned quite a bit on inductors, and I've never seen them being used in like this workshop or in mine. And I just wondered, like, when are those like actually used?
Yeah, so they're of the three fundamental elements, capacitor, resistors, and inductors. Those are probably the least used, particularly with these types of things. So they also store charge like capacitors, but in practice, if I can make a filter with an inductor, I can make the same filter cheaper and smaller with a capacitor. But they are good with power circuits. So if you ever get into power electronics, they're used a lot there because they essentially are short circuits at DC, which is what the power supply voltage will be, is at DC, and high impedance at high frequencies, the opposite of capacitors, and that's just more conducive to working with power circuits than with just making general purpose filters.
Okay.
So in practice, they'll in general they'll be larger, they'll be more expensive, so they're less practically used for things like filters in just like standard analog circuits, which is what we've been doing. But with power circuits, they're all over the place. With circuits, the high frequency circuits, 1 megahertz and above, they'll be all over the place there. But low frequency circuits, low frequency and low power, 10 kilohertz and smaller than 1 amp, not so much.
Okay, that makes sense. Then my last question, I remember this one. So like I learned all like the technical derivations and equations for it, but what like essentially is impedance?
So an impedance is, you get the idea of resistance, right?
Right.
So it's a resistance at different frequencies. So it's like 1 over omega C or omega L, right?
Yeah.
So I'm not wonderful at this stuff either. But just if you just imagine there, so the capacitor changes with frequency, just because of how it's constructed. So the impedance is the quote-unquote resistance at different frequencies. So if I have an AC current, how much does it impede, an AC current?
Okay, so it's like a variable resistor almost.
Sort of, yeah, but the variation is based on frequency.
Okay. And is that bound in like all components, or is it capacitors?
Capacitors and inductors.
Okay.
And it has to do with the fact that they're time varying, so they charge. So that's kind of why that is the way it is. Versus resistors are not time varying.
Right. Okay. All right. Yeah, I can't really think of any more questions now.
It's all right, dude. Cool deal.
Well, I will. I'll leave the circuit as it is right now for the heart rate monitors, but I can build the other one that you were doing sometime.
Sure. Yeah, I'll finish doing up the fritzing, and I'll just put it out there so you can take a look at it whenever you're ready.
Okay.
And let me know when you
like I said, I didn't know. I don't know if I'll be able to make it tomorrow because I've got a lot of packing to do.
That's all good. Seems like this will be our last day anyway. It was fun.
It was. I learned a lot this time. I'm not gonna lie.
Cool. Glad you did.
Alrighty. Well, have a good evening.
All right. You too.
See ya.
Peace.